Hi everyone, and welcome to picking the right machine learning model for your data. As always, please leave feedback, like, and subscribe for more videos like this. All right, so let's jump right into it. To make picking the right machine learning model easy, I've made this decision map of questions and answers. I know seeing all of it at once is overwhelming, so let's digest it step by step. So let's start. Are time and/or dates one of the most important components of your data? If yes, am I modeling time to an event? If yes, then I'm doing a survival analysis. And despite the name, this has nothing to do with survival of the fittest or evolution. This is a type of model that models time to an event. Some examples of this could be recidivism for offenders who are released from jail, where you're modeling how long it takes them to commit another crime and return to jail. Another example of this could be after a patient is discharged from a hospital, how long does it take for them to be readmitted? So that's survival analysis, but say we're not modeling time to an event and the answer to that question is no. Then we would be doing time series. And the next question would be, is my data stationary? And stationary data means that you don't have a seasonal component to that data. If yes, and it is stationary, then you can consider doing a moving average model, which is just like it sounds, it's a series of moving averages across the span of the time series. Or you can do an ARIMA model, which is an autoregressive integrated moving average model. And examples of stationary data could be your O2 levels in the blood or your heart rate, for example. If we don't have stationary data and there is a seasonal component to it, then we would answer no. And we would use either a Holt-Winters exponential smoothing model, which decreases the weights of the data the further back you go, which makes sense, of course, because data years ago might not be as relevant as data from yesterday. Or you do a SARIMA model, which is a seasonal autoregressive integrated moving average model, which is basically your ARIMA model, just with that S, that seasonal component to it. And examples of non-stationary data or anything with a season to it would be things like sales, which may pick up around the holidays, temperatures, which are certainly seasonal, or maybe number of houses on the market, which is generally higher in February and March. And so this is if we have time or dates in our data. And there are certainly other models and other analyses that involve time, such as a difference in difference analysis and so on. But this is really a good list to get started. But what if time and dates is not our main focus or the main thing in our data and we answer no? The next question regarding our target is regarding our target variable. So do we have an outcome, a target, a dependent variable clearly identified in the data? If yes, then we're going to be doing supervised learning. The next question then is, what does that target outcome dependent variable look like? Is it continuous or discrete? If continuous, then the next question is my data linear? Does it have a linear relationship? If the answer to that is also yes, these are going to be my main options. If my independent variables are also continuous, we're going to be doing a multiple linear regression. And now let's say we have a lot of variables to choose from, and instead of doing something like a forward, backward, stepwise selection process, we want to throw all of those variables into the model. We could do either a ridge regression or a lasso regression, which will then penalize some of those variables with the L1 or L2 penalty term. Or we can do an elastic net, which combines both the ridge and the lasso regression and those penalty terms into one model. If our independent variables are categorical, we would do an ANOVA, which is an analysis of variance. And if our independent variables are continuous and categorical, we're going to be doing an ANCOVA, which is an analysis of covariance. But what if your data does not have linear relationships and we answer no? Then we're going to be doing the following regressions. We have a decision tree regression, and a decision tree basically creates a hierarchical tree with decisions and consequences. And it's a fairly simple model and is easy to interpret and understand. We can do a regressive random forest, which is a model of multiple decision trees, and this performs quite well, but takes a little bit more computational power than a decision tree, and it's a little bit harder to interpret. We can do boosting models like gradient boosting, XGBoost, AdaBoost, which are ensemble models. These use a bunch of weak models to create a super powerful model, and each weak model learns from the previous one. XGBoost generally outperforms AdaBoost and gradient boosting, but AdaBoost is easier to understand and interpret. We have support vector machines, which uses one or more hyperplanes to divide data, and it looks for the maximum margin between data points so it can draw that hyperplane. We have k-nearest neighbors, which finds similar data based on distance from other data. So I always like thinking of it as forming little neighborhoods of data by finding the nearest neighbors. And we have a neural network. And a neural network is really only appropriate when you're doing really complex pattern recognition. And the way a neural network works is it has an input layer, it has one or more hidden layers, and then an output layer. And each of the layers is connected to a bunch of nodes. And those nodes are connected to each other and the layers, and the connections have weights associated with them, and then the nodes kind of aggregate those weights. And most of these models will accept both continuous and categorical data with scaling or normalizing of that data. And so these are the models for supervised learning where our target variable is continuous. But what if it is discrete? So let's say, what does the dependent variable look like? And we say it is discrete. This means instead of a regression model, we're now doing a classification model. Most of the models are the same as the list we just went through, but instead of a regression, you're now doing a classification. There are two additional models that are added to the list. First, we have a logistic regression. And this is a binary classification model, which models the log odds of an event. It's still a linear model because what you're basically doing is taking that binary output or the binary data, and you're applying a log transformation to it, which makes it linear. And even though this is called a regression, you're really doing a classification problem. And then the second model that we're adding to the list is the naive Bayes model. And naive Bayes is really interesting. It uses the probability of an event, but then also the conditional probability of that event. And this is a generative, not a discriminative model, which means the model is learning from the data and learning the data versus the boundaries between them. Like I said, the rest of the models we really just went through. Instead of doing a regression, we're now doing a classification because our outcome is discrete. All right, and so these are all of the models that we have for supervised learning, but say we don't have labeled data. And we answer no to whether our data is labeled or we have a clear outcome, target, dependent variable. That means we're going to be doing unsupervised learning as opposed to supervised. And if we're doing unsupervised learning, I would start with these three options. So we can use a clustering algorithm. I think one of the most common ones is k-means, but there are definitely other ones, things like hierarchical clustering, Gaussian mixture model, centroid clustering, dbScan, and so on. And clustering, I think the most I've seen that is using it to build personas of clients, personas of patients, personas maybe for shopping. So that is clustering. We can do an association analysis. And if that's what we're looking for, it reveals patterns behind our data and it's easy to interpret. And this is really interesting. It can be used, for example, to upsell something. So, say someone online buys dog food. And based on your association analysis, you know that people who buy dog food oftentimes also buy treats, a dog bowl, a water bowl, maybe a little mat for under the dog bowls. So this would be an association. If they do this, they also do, if they do A, they also do B, C, and D. And lastly, we have dimension reduction. This includes things like principal component analysis, which is really common in text analytics and image recognition. We have singular value decomposition, and then things like autoencoders, which use an artificial neural network. And it basically encodes your data to a lower dimension and then decodes your data back to that higher dimension, which is pretty cool. So this is my list of algorithms. This by no means is every single machine learning algorithm or analytical tool out there. But if you're familiar with these, you can probably build a model to answer most questions that you'll come across at work or for fun projects. And really, the key to these models is hyperparameter tuning. So once you have a base model, you can really tune it to be super detailed. And of course, we don't want to overfit, but I think hyperparameter tuning is key to making these models really successful. Thank you so much for watching, and I hope this has been helpful for you in determining which ML model to choose. Thank you, and please leave feedback, like, and subscribe for more videos like this. Also, if you have any video recommendations, please leave those in the comments.